Let's look some more at these two cases here. Our car driving out of the page, taking that left-hand turn, and then our bug sitting on the disc riding around on this record player as it spins. I've drawn these two kind of from a side view where we're seeing the vertical direction like this and the radial direction like that, but the tangential direction would be kind of out of the page. So let's instead draw these from a top-down view. Like this. So here's looking down from above, kind of a bird's eye view on the car taking that same left-hand turn. So our car's velocity is down in the tangential direction, so its velocity at the moment is there, tangent to the circle. That was the out of the page direction here, car's velocity coming out of the page at you. And so our vertical direction, the z direction, now that's out of the page. Now this is our z direction coming out of the page, so we can't see that. So instead we've got our radial and tangential axes there. So blue is the circular path of the car as it's taking this left-hand turn, and the force that will be responsible for doing the turning, and also, of course, always for speeding your car up or slowing it down, is static friction between the tires and the road, or in the bug's case, static friction between its feet and the surface of the disc. That's our traction. Traction does everything for us, speeds us up, slows us down, and turns us, as long as we're not skidding or slipping or sliding. So our force of static friction could point in pretty much any direction. If it's pointing like this, that would indicate that we are both turning and speeding up. The radial component of that force of static friction, pointing in towards the center of the circle, that would be responsible for turning the car. But this tangential component here of our force of static friction, that would be responsible for speeding us up. So if there's a component of friction parallel to our velocity that's speeding us up, this component perpendicular to the velocity, that's going to be turning us. So we've got the speeding up and the turning in this particular instance. So here's our equations of motion over here, our Newton's second law. We would need to break up that force of static friction into its tangential component and its radial component. Here, summing the forces in the z direction, that's the direction we're not seeing from this top-down view. Z direction is out of the page. So in the z direction, we know we've got our normal force and our force of gravity, which are balanced. We're seeing that clearly from this side view here, normal force and force of gravity balanced. Okay, so we can conclude Fn equals mg. Then going to the radial direction. The net radial force, that will be the radial component of our force of static friction. So this right here, the component of our traction like static friction force between acting on the tires from the road, pointing in towards the center of our circular path. So in the negative radial direction, that's our centripetal force there, and we set this equal to minus v squared over r. So we've got that result and that result to work with. Furthermore, in our tangential direction, note that we've kind of got three dimensions of interest here for horizontal circular motion: the z direction, the r direction, and the tangential direction. So we need three separate instances of Newton's second law, one for each direction of interest. So the tangential direction, we sum the tangential forces. That will just be the tangential component of our static friction, if there is one, FFST here. So that would be the traction responsible for helping the tires grip the road and speed forward through the turn. And we'll set that equal to alpha times r, our radial acceleration times r. Recall that our radial acceleration here, alpha, is the rate of change of our angular speed, omega here, our rotation rate as we rotate around this circular path. So the tangential acceleration, that speeds us up, slows us down, increases or decreases our rotation rate. Okay, so this is in general what could be happening here. I want to ask a specific question. What is the maximum speed at which you can take that turn without skidding. You know that if you're going too fast and take a tight turn, the car might skid forward instead of successfully taking the turn. So what's the max speed at which you can go? We can address this question by first setting the tangential component of our force of static friction equal to 0. So let's just say that we're going to take this turn at a constant speed. So set this equal to 0 right here. So we have no tangential acceleration. At is 0, so our speed is constant. Okay, so we're not worried about speeding up at the moment. Let's just say we're going at some constant speed. What's the maximum constant speed at which we can take that turn without skidding? So if we're not going to skid, then we want to maintain contact, maintain our tires sticking to the road. So not skidding, not slipping, not sliding. We want static friction, not kinetic friction. We don't want slippage between our tires and the road. If you're slipping, you're skidding. So then we know our static friction has a maximum value that it can achieve before slippage occurs. So if we want to find the max speed you can take, we want friction to be working as hard as possible to prevent that slippage. So we're going to set friction equal to its maximum value. Static friction equal to its maximum value, mu s times Fn. Mu s here, that is determined by the material of your tire and the material of the roads. That's material property right there. Okay, so up here, we're going to set the force of static friction in the radial direction equal to mu s Fn. We're going to max it out. So then rewriting this equation, replace FFSR with mu s Fn, set that equal to minus Vmax squared over R, and then our normal force is equal to our force of gravity, as we showed up here. So we have to show this step first so that this substitution down here into this equation makes sense to the reader, that Fn becomes mg because of our earlier analysis of N2L in the z direction. Then masses cancel, and we can rearrange to get this expression here. The maximum speed at which you can take that turn depends on gravity, depends on the size of the turn, and depends on your tire material. Note what it doesn't depend on, the mass of the car. That cancels out. So you can load up the bed of your pickup truck with a bunch of extra gear, and that's not going to change the maximum speed at which you can take a turn. The mass of the vehicle doesn't matter. What matters is your tires. Mu s right there. That tire material determines how much traction you get. Tires matter. And then, of course, the radius of the turn matters. Because if you're trying to take a tight turn with a small radius, you'll have a smaller maximum speed without skidding. As for our bug back here, we know that if the disc spins too rapidly, the bug is likely to slip and skid off in the direction tangent to its path at that moment. So there will be a maximum rotation rate for our spinning disc before the bug flies off. So let's find that. Basically, the bug's FBD is the same as our car's FBD, so all our prior analysis here applies to the bug as well. So what's the max rotation rate for our record player? Well, this maximum speed at which the car could take that turn, that's also going to be equal to the maximum speed that the bug can have before its feet slip on the disc and it goes flying off. So we can find our maximum rotation rate just by setting the bug's maximum speed equal to its maximum rotation rate times r. V equals omega r. So the omega max is just the Vmax divided by r, and we get this expression. So r would be the radius of the bug's path, not necessarily the radius of the disk, and omega is the rotation rate for that spinning disk, measured in radians per second here. So there we go. If the disk spins any faster than this, bug goes sailing.